Welcome to the OpenMP SE20 Booth Talk series. My name is Ruud and I work at Oracle in the Oracle Linux Engineering Organization. I am a performance engineer and I look at application performance, but my main focus is on tools for performance analysis. And in this talk, I'd like to share with you my experiences with OpenMP and performance. In particular, I'd like to show you ways how to get good performance out of your OpenMP program with a minimal effort. There's always some effort needed, there's no escape, but as I will show, it's really minimal and the impact can be tremendous. So stay tuned and let's get started. There's a common and persistent myth that OpenMP does not scale. I still hear and see that way too often, and it's just too simple to be true. OpenMP is a programming model. A programming model in itself cannot not scale. Think about it. It's like when you want to cook a dish and you have your recipe and your ingredients. If you mess up on the ingredients, then your recipe will fail. The dish you prepare will probably taste horribly. And it's the same with OpenMP. OpenMP has the ingredients for you to create a parallel program. You have to use the right ingredients and you have to use them in the right way in order to have a successful parallel program. So what cannot not scale, what can be in the way of your scalability are a couple of things. Could be the tools that you use. For example, the compiler may have a performance glitch. There could be an issue with the library that you're using. Maybe you're using an OpenMP runtime that has a feature that's not very well matured yet, and it pulls your leg. Although not likely, all these things are possible and should not be excluded. Another reason could be at the hardware level that there's a mismatch between the system that you're using and the resource requirements. For example, let's say your application is very bandwidth hungry. You need lots of bandwidth. As you're adding threads, at some point, maybe the system that you're using cannot sustain the pressure on the memory system anymore, cannot deliver the bandwidth that you need, and as a result, the scalability will suffer, and your program will stop scaling, and in the worst case, the scaling will go down as you add threads. These are all things that can happen. What I see in practice, though, is the most likely culprit here is actually you. The user makes a mistake, violates an OpenMP performance rule that you don't know, but you violate it, and as a consequence, the performance will suffer. In this talk, I'd like to give you those rules. I'd like to give you the rules, the tips and the tricks, how to get good performance out of your OpenMP program. So we're going to talk about the basics. And if you follow the guidelines that I'm going to give, you should expect decent performance. And an OpenMP compiler and runtime system should do the right thing for you. You may not get blazing scalability to thousands of cores, but it definitely gets you going, and you should expect, again, decent performance. Certainly, if you ever have to go to the OpenMP performance court, the lawyers there will not have any case against you. The ease of use of OpenMP is a mixed blessing. It's great, things just work as you would expect them. Ideas are easy and quick to implement, and it gets you going very quickly. But some constructs are more expensive than others, and you may not know that, but you have to know. You have to know what is the right sort of tool that I can use to solve my parallel computing problem. And if you pick the wrong one, then performance may suffer. So again, that's what I'm going to talk about in this presentation. Also, if you write dumb code, you probably get dumb performance. Actually, I can make that stronger. You will get dumb performance. The reason is that OpenMP is very prescriptive. You tell the OpenMP compiler what to do, and it will do so. It will follow what you tell it to do. So if you have some dumb advice, the compiler will follow the dumb advice and generate bad code. And for compilers, it's very hard to fix that. Sometimes it's impossible. Sometimes the compiler technology isn't there yet to help you fixing things. So the responsibility is on your shoulders. In any case, don't blame OpenMP, please. In the next section, I'm going to give you tips and tricks how to avoid writing dumb code. And as you will see, this will get you very, very far in achieving efficient OpenMP. It all starts with single thread performance. It's often overlooked, but you really have to pay attention to that. And the reason is very simple. What do you think? If your code performs badly on a single core, what do you think will happen on 10 or 20 or higher core counts? My claim is it'll get worse. And the reason is that very often poor performance on a single core means poor memory performance. You're not using the memory system and the caches in the right way. Well, when you multiply that with 10, say, so you're running on 10 cores, that will just get worse. You put a lot of burden onto your system interconnect, and your code will stop scaling much sooner than needed. So again, don't forget about single thread performance. Also, remember, scalability can mask poor performance. It happens to be that a slow code scales better. The reason is very simple. The overhead that comes with parallel computing is less dominant. But at the end of the day, although it scales better, that code may still be slower, and often it is. So don't be blinded by scalability. Always look at the time to solution as well. I'm now going to give a set of basic rules that applies to pretty much everybody in every application. The first golden rule is do not parallelize what does not matter. That seems so trivial, but too often I see people parallelize parts of their code that really don't matter. Now what you need to do is use a profiling tool. Pick whatever you like, I don't care, but let the profiling tool guide you where you spend most of your time. And that's where you start parallelizing. Don't parallelize something that does not contribute to the total execution time, because you even run the risk that the parallel computing introduces overhead that will make that part of the code slower, because there's not enough work done to compensate for the overhead. So always use a profiling tool. That'll tell you where the time is spent, and that's where you start parallelizing. Another golden rule is don't share data unless you have to. Sharing data is a really great feature in OpenMP, and it's very convenient. But in some cases, there's a cost associated with it, a performance cost. And the best advice I can give is use private data where possible and only share data when you have to. That simple rule already helps in addressing OpenMP performance issues. Another one is that one parallel 4 is fine, multiple back to back, that's evil. And I'm going to say a little bit more about that soon, but that's another thing that I see in too many applications, all these parallel for loops or do loops in Fortran, back to back. That's really a bad idea. Another golden rule is think big and maximize the size of the parallel regions. What do I mean with that? Ideally, you have just one parallel region, and all the work is concentrated in that. And the reason is because a parallel region is relatively expensive. It also ends with a barrier, and a barrier is potentially very costly, so you want to minimize those, and you do that by maximizing the size of the parallel region. Try to have as little parallel regions as possible, and put as much work into a parallel region as you can. And here's an example of what I meant with those parallel for loops. Let's say you have a bunch of loops and they can all be parallelized. You will get the right result when you do that. It's very tempting to use a pragma OMP parallel for and parallelize each individual loop. I've seen that in numerous codes, and in as many numerous codes, I've fixed it because it's a bad idea. Think about the cost associated with the parallel region. Well, each parallel 4 is a parallel region, so you get that cost. So each time you get there, you'll get that cost. And what's probably even worse, there's no potential for the no wait clause, which is a really very powerful clause to omit the barrier at the end of the construct. Since you cannot have a no wait on the parallel region, the parallel 4 is stuck and has all those barriers. A really bad idea. This is a much better approach. There's one single parallel region, OMP parallel, and inside that parallel region you have your pragma OMP4 to parallelize those loops. Now note, that should not be OMP parallel 4 inside the parallel region. That's nested parallelism. That's completely not needed here and will have disastrous effects on performance. You just have a simple pragma OMP4. So you have the parallel on the outside and the OMP4 on the inside. It also opens up opportunities for the no wait. As you probably know, the no wait omits the implied barrier at the end of a construct. And sometimes that barrier is not needed. Barriers are there for safety, and sometimes you need them. But OpenMP by design is a very safe language, and it inserts a barrier where it may not be needed. And with the no wait clause, you can get rid of it. Certainly, the one at the very last loop is redundant because there's a barrier at the end of the parallel region anyhow. Now, admittedly, a smart compiler could do that for you, but I don't think compiler technology has progressed to the level that it will actually remove that no wait, that barrier, sorry. So it's better for you to include a no wait and at least shave off one barrier, but maybe even more. Again, you get a cost only once, and there's more opportunities to use the no wait clause. It performs much better, and you'll be surprised how much better. A little bit more about parallel regions. As I already said several times, a parallel region carries a relatively high overhead. And the goal is to minimize the number of times a parallel region is encountered. Why do I say that? I see too many nested loops where deep inside the loop nest you'll find a parallel region, maybe a parallel for or parallel do in case of Fortran. Well, that's a really bad idea because that parallel region, the overhead with that, and the barrier are executed each time you go through the outer loops. And that could be many, many times. One sort of classical trick is to push that parallel region outward and embed the whole loop nest in a parallel region. There are examples out there that will show you how to do that. A little bit more on the basics. Again, the no wait clause, as simple as it is, it's extremely powerful. Barriers are expensive. You don't want them unless you need them. So identify where you can use the no wait clause. You're probably not going to do that in the first OpenMP version of your program, but once you have it running, you have the correct results, try to see if you can use the no wait clause and get rid of those barriers. The one thing you got to watch out is, of course, don't introduce data races. So do this with care, do this one by one, and make sure you get the correct results, because it is easy to introduce a data race that way. Another powerful feature is the schedule clause. In case you have load balancing issues, not all threads perform the same amount of work, the schedule clause with the options like dynamic and guided can do magic. And again, you'll be surprised how much you can gain by just changing the schedule clause on your parallel for loop. So again, think about that. For all these things is use a profiling tool. You have to use a good profiling tool and find those opportunities, find out about load balancing, find out where barriers are, and tackle them. As I've said several times already, every barrier matters. You need them, they are needed, but use them with care. The same is true for locks and critical regions. Critical regions are pretty much needed in every parallel program, but depending on what you do in the critical region, an atomic operation may provide the same functionality, but at a much lower cost. Atomic operations are much more efficient than fully blown critical regions. So think about atomic operations as a good alternative, for example. And again, minimize the locking and the critical regions as much as you can. At the end of the day, everything matters. There is Amdahl's law after all. So every small overhead gets out of hand very quickly and sooner than you like. And when you think about it, Amdahl's law applies here. For example, a critical region tends to serialize the operation. So you have a serial part in your program. Well, Amdahl's law tells us that that part dominates very quickly. So use those constructs to get the right answers, but use them with care. The list I've just given gets you going. It's actually surprising how much you can gain by following these pretty simple guidelines. but that's what I call the low-hanging fruit. It's there, and for you to handle it. There's some fruit that's actually a little bit higher up the tree. Still very, very important to tackle, and it's all about memory access. So in the second part of this talk, I will cover that. The good thing about OpenMP is that memory access just happens. You need access to a variable A, you'll get it. The system will take care of it. So that's really good. There are two things to watch out for as you access your data. They're called non-uniform memory access, NUMA for short, and false sharing, and I'm going to explain them in the next couple of slides. Before I do that, I want to explain that both have nothing to do with OpenMP. They're characteristic of using a shared memory architecture. It goes back to the way a shared memory architecture is built. And if you would write the same construct in pthread, say, and you'll suffer from NUMA and maybe false sharing as well. So again, this has nothing to do with OpenMP. You're using OpenMP though, and these are real things. NUMA is real, false sharing is real. So they may impact your OpenMP performance, and I'm going to say a little bit more about that. This is a diagram of a generic, common, contemporary NUMA system. In other words, this is what many systems look like out on the market today. And I'm showing you a system with 4 nodes. There are 4 nodes. What we see, the green boxes are the cores. So each node has a set of cores. The purple box is LLC, the last level cache. Underneath, there could be lower level caches, but there's always a last level cache that connects to the memory. But the most striking thing in this picture is that memory is physically distributed. Each node has 1/4, 25% of the memory. So a node owns a portion of the memory. The magic happens in that cache coherent interconnect. That knows what's happening in the system, and if you need your variable A, it'll figure out where it is, and it'll get it to you. So that's really beautiful from a programming point of view. You don't know that the architecture is highly distributed under the hood. To you, it appears as a whole bunch of cores and one big memory. Underneath, it's different. So this is what I call the developer view. You got your threads, you have your memory, where your data is, and there's some magic that glues it all together. So when you use an operating system command to tell you what the system looks like, for example, you use top on a Linux system, it'll just show you how much memory you have and how many threads are running, and it won't show you what's going on. There are Linux commands that will tell you, but the system view is what we call a single system image. There's one memory, and there's a pool of threads. But again, under the hood, it looks different. So the way to describe NUMA is that memory is physically distributed, but logically shared. It's scattered over the system. You don't see it. To you, there's one memory. You share data in a transparent way. All threads can access the shared data, again, regardless of where the data actually is. So you don't know where the data is, and it doesn't matter for correctness. You will get the data, but it does matter for performance, where your data is. And that's shown in this diagram. I have my thread, that's the purple box, executing somewhere in the system. Okay, so it executes over there. And if it needs some data, the good case is where there's local access. The data is in what we call your local memory, the part of the memory connected to where your program is executing, where your thread is running, I should say. That's the fastest way to access data. That's the optimal case. That's the goal. But what could happen is that the data is further away. And on large systems, it could be really far away. This is like what we say one hop, but it could be multiple hops away. And it can take a while to get your data. And when I say takes a while, that's of course on the scale of things. While the system is fetching your data, you could do a lot of computations, for example. So it's wasted time. And with NUMA, what you'd like to do is avoid this situation as much as possible. Whenever a thread needs the data, it should be as close by as possible. That's the goal of NUMA tuning. Now, whether you like it or not, NUMA is here to stay. The reason it was introduced in systems was that it provides more scalable bandwidth. As you add nodes, you add bandwidth. And for example, a benchmark like Stream exploits that and shows you how much you can get out of the system. And those are usually very impressive numbers. And the reason is that Stream benchmark has been optimized for you to get local memory access, not remote. You as a developer may have to look into that as well, depending on how sensitive your program is to where your data is in the system. Certainly, as core and in particular node counts go up, NUMA increasingly matters. It's not something you can ignore. Hopefully, your application is not sensitive to it, but if it is, then you have to consider it. The good news is that OpenMP has great support for NUMA. It's a very extensive set. The feature continues to be expanded in subsequent releases of the standard. So OpenMP has something to help you out. Unfortunately, it's beyond the scope of this talk to talk about NUMA tuning, but just know there's a lot of information out there and OpenMP has NUMA support to help you master that architecture. The last thing I want to talk about is false sharing. False sharing is actually one of those things that's at the end of the checklist. You start looking into it if nothing else explains your scalability issues. It's one of those things that may happen. It's not very likely, but you can't exclude it, so it's better to know about it. False sharing occurs when multiple threads modify the same cache line at the same time, and it's important to understand that all three conditions have to be met. So we talk about multiple threads. There's a relatively small portion of data that's updated at the same time. For example, multiple threads access different portions of a vector, but that vector is very short, so they're all hitting on the same cache line or cache lines. That's when false sharing occurs. Why is that so bad? Well, this results in the cache line to move through the system, because each time you do an update on a cache line, you need to have that cache line in your cache. So if it was elsewhere because of a previous update, it will have to travel to you. You do your update, and then the next one will do the same. So history repeats. And as a result, the line starts ping-ponging through the system. And that's expensive. That costs time. There's an additional cost. Each cache line has status bits. There's a cache coherence protocol that explains what states there are and how you transition between states. Updating those bits takes a little bit of time, but that's a secondary issue compared to the line ping-ponging through your system. That's the biggest thing to worry about. Now, false sharing happens throughout the execution of the program. And if it's not too frequent, that's okay. That just happens once in a while, and that's fine. It's not okay if this happens very frequently. If it's in the heart of your algorithm, that's when you have a noticeable impact on performance, and you should look into false sharing, trying to fix it. Here's an example. There's a parallel region, and the parallel region assigns 0 to a vector, and that's executed in parallel by multiple threads. And the index into the vector is given by the thread ID. So essentially, each thread initializes one element of the vector to 0. Why is that bad? Well, we just described the conditions for false sharing to occur. It's a short vector spanning just a few cache lines, maybe one or a few more. And the line is modified. The elements in the line are modified. So this has all the ingredients for false sharing to occur. And the line will start moving through the system. And here's an example on 4 threads. We have 4 threads. The vector A is 4 long. Time is from top to bottom in this diagram. And we'll start with the first update. So thread 0 presumably does the update. It will get the cache line that A0 is part of, and it will do its modification. That's fine. The next one may be done by thread number 3, and that means that wherever thread number 3 is executing, the line will have to move to. So the cache line will move wherever it is, and then it can do the update. Likewise, for thread number 2, again, the line could move throughout the system, and finally, the last one. So throughout this process, the line is ping-ponging through the system from cache to cache, and that takes time, and that slows you down. And in my experience, false sharing, if it happens, is usually pretty bad. So here's your homework. Follow the guidelines I've just given, and in this order, sort of. I started with the low-hanging fruit. Those are all really easy things to do, I think. Certainly easy to do some experimentation, give it a try, and you'll be surprised. A small change can give you a huge boost in performance. Give it a try, but always make a profile before and after the change. You profile your code, you tackle a certain part of your program, and you profile again to see what happened. And the reason is that the devil is in the details. Details sometimes make all the difference, and maybe something doesn't work out as you might expect it. So always check with your favorite profiling tool. And eventually, if you still have a performance mystery and you can't explain poor scalability that you're seeing, start thinking about NUMA. It could be that NUMA is affecting you. And once you have eliminated or tackled NUMA, you still see scalability problems. It could be false sharing. In the worst case, you have both, but hopefully not. NUMA is much more common than false sharing, but again, you need to consider both. So thank you for your attention. As always, stay tuned, and remember, it's not that OpenMP doesn't scale, it's that bad OpenMP does not scale. Think about, remember that, please. Before you go, there's one more thing I wanted to point out. There's a really good website, openmp.org. That's where you find the specifications. There's a forum for all your questions. There are reference guides. There's a lot of material. There are blog articles, papers. So please check out openmp.org. It's a great source of technical information about OpenMP. And specifically, the videos and PDFs of these OpenMP SE20 presentations in the Booth Talk series will all be posted and made available on the website mentioned here. So enjoy, good luck, and on to the next time. Bye-bye.